būtums.
Okay, so is that good?
Yes, it's good. We are live. You can start, Steve. Thank you.
Okay, all right. Well, thank you for joining me this afternoon or this morning, as the case may be. It's a privilege and an honor to be here to talk about lessons learned from COVID-19 forecasting as they apply to software estimation. I thought I'd start by just describing how I got interested in this topic. My role in COVID-19 forecasting really is derived from my interest in software estimation. And way back in 2006, when I published my software estimation book, I made the observation that experts tend to use simple estimation strategies, even when their level of expertise in the subject being estimated is high. And I definitely found that to be the case in COVID forecasting as well. And the interesting thing about this is the level of expertise in infectious diseases or other kinds of medical knowledge is just off the charts. It's extremely high, but the fixation on forecasting techniques that really have, I think, a dubious track record has, I think, persisted through the pandemic. So I started estimating using my own software-based estimation practices. And I started checking how my estimates were doing or my forecasts were doing compared to those I saw published in the news. And to my surprise, my forecasts were actually doing pretty well. And so that got me interested in forecasting more officially. And that got me involved in contributing forecasts to the CDC, which is the organization in the US, the Centers for Disease Control, that has been responsible for COVID forecasting. So if you go to the CDC website and you go to the COVID-19 forecast page, as shown here, and then you go look at the national forecasts or the state forecasts, and you zoom in on who's contributing, you'll see my model, which is COVID complete, and this is the most recent week's forecasts. So you'll see that COVID complete's forecasts for this week are as shown. I'm on the low end of the scale, but the purple line that is directly above mine, which maybe you can see and maybe you can't, that is the Ensemble forecast, which is the forecast of record for the CDC. So I'm a little bit lower than the Ensemble, but definitely on the low end overall. That said, my forecasts have been among the more accurate, and I'll say a little bit more about that in a minute. So I think starting with some really basic concepts, I would make a distinction between the concepts of estimate, forecast, and speculation. And really, sometimes in the software world, we've seen a lot of discussion over the last several years in an agile context about let's not estimate, let's forecast. I have mixed feelings about that comment because a forecast is simply a future-based estimate. So if I'm trying to make a guess about the number of fish in a pond, that's an estimate because it's now. But in the future, if I was going to estimate the number of fish in a pond a year from now, that would still be an estimate, but it would also be a forecast. And in software, I estimate or forecast things like how many iterations my next release will require and things like that. Forecasting is not the same as speculation. And we have a history not just in software, not just in COVID forecasting, but in virtually every area in which people make forecasts of speculations being treated as forecasts. There's a really interesting book called Super Forecasting that talks about the fact that a lot of people who make high-profile forecasts never close the loop on assessing are their forecasts accurate or not. And a lot of times the forecasts are baseless, they're not accurate, but no one ever actually looks at whether what the track record is. And so that's something that I will talk about in a few minutes as well. So really the basis of forecasting or estimation is things we already know. If we're just piling guesses on top of guesses, then we're not estimating or forecasting, we're speculating. And so really we have to start with something that we know. Ideally, it's something that we can actually measure or count. If we're estimating the thing that is the basis for some other estimate, then that really drifts into the area of speculation. So turning to the specific topic of CDC COVID forecasting, the CDC forecasting group and approach looks like this. The CDC work is overseen by a team at the University of Massachusetts Amherst, and there are a number of modeling groups that submit forecasts to the CDC. Over the course of the pandemic, there have been about 60 different groups that have contributed forecasts at different times. Any given week, there are about 30 groups that contribute forecasts. As time has gone by, there are some groups that drop in for a few weeks and then drop out, but the persistent core at this point is maybe about 25 groups, of which my forecast is one of those groups. The specific organization at UMass Amherst is Reich Labs, which is based in the Department of Biostatistics and Epidemiology. And the way they assemble the Ensemble model is to take forecasts that meet certain criteria and then simply take either the average, the mean, or the median of those forecasts to come up with the Ensemble forecast. There's been quite a bit of work over the months about trying to come up with an approach that works better than a simple median or a simple mean. But up to this point, constructing the Ensemble out of the simple median, which is what's currently being used, has worked as well as anything else. And there at any given time, there are other candidate models that are in play, but that's really the one that's in play officially right now. So each week, each of the team contributes quite a bit of data. As I said, about an average of 30 teams per week. Each team contributes forecasts for the U.S. national level, for the 50 U.S. states, and for the District of Columbia. And I will also say that this has been going on for about a year now. Europe adopted a similar Ensemble forecast approach that began more recently than that, and there are quite a few teams that are contributing, that had been contributing to the U.S. forecast, that are now also contributing to the European forecast. I am not one of those, and so I can't speak to that very knowledgeably. Each week, each team contributes forecasts for 1, 2, 3, and 4 week horizons. Each team contributes incremental forecasts, meaning the forecast only for week 1, only for week 2, only for week 3, and only for week 4. Each team also contributes cumulative forecasts. So basically, pandemic through the end of the next week, pandemic through the end of the next 2 weeks, pandemic through the end of the next 4 weeks, and so on. Each team contributes forecasts for a significant number of quantiles. So the quantiles range from 0.01 to 0.99. So basically 0.01 is the 1% chance that the actual result will be below that forecast. The 0.025 quantile is the 2.5% chance that the quantile will be below that forecast. 0.5 is essentially the point forecast, the nominal forecast, the 50% likely forecast, and so on. And so in total, each team contributes about 10,000 forecasts per week. When you take the number of quantiles, the number of areas that are forecast, the number of forecast horizons, cumulative and incremental, you end up with just under 10,000 forecasts per week. So what I analyze, and as time has gone by, I'm still contributing forecasts into the Ensemble model, but my emphasis really shifted over time to evaluating the forecast, mainly because I did see others doing that, and that seemed to be part of what got me interested in this in the first place, was just closing the loop and making sure that that we actually were looking at, are the forecasts any good or not? And so what I analyze is a subset of this forecast data, and that is the forecast for the U.S. national forecast, the 50 states plus DC, the 1, 2, 3, and 4 week forecast horizons, but I only look at the incremental forecast, cumulative, from the date of forecast, not from the beginning of the pandemic, but from the date of forecast. And then I look at a subset of the quantiles. I look at the point forecast, which is the 0.50 quantile, the 50% prediction interval, or PI, which is the range from the 0.25 to 0.75 quantile, the 95% prediction interval, or PI, forecast, which is the range from the 0.025 to the 0.975 quantile. And this subset ends up being about 625 forecasts per week per team. Since the pandemic has been going on for too long now, but the data has been being produced since the beginning of July. What we have at this point for data analysis purposes is we have about 6,500 forecast sets with about 625 forecasts per set, and that gives us a total of about 4 million forecasts where we can compare forecast to actuals up to this point in the pandemic. And what this means is that we have this incredibly rich data set where we've had at times 60 different teams contributing forecasts into this pool of estimates versus actuals, and 4 million total forecasts. And so we get to look at all kinds of things in this data set. We get to look at how accurate are different methods, how do the different teams address uncertainty in their forecasts, how well do they address uncertainty in their forecasts, are there some models that tend to do better than others, or is it just kind of a mishmash of some do well sometimes and some do well other times? Lots and lots of interesting opportunity to explore estimation effectiveness in this context. The slides will be available at some point after the session, so if you're interested or if you just want to do a screen capture on this, you can take a capture of some URLs that everything I'm talking about is public information. Most of it's available on GitHub in some place or other. Some of it's available on US government websites, and some of it's available on my own personal website. But there's an ability to dive into the data as deeply as anybody wants to on this. And there will be for the foreseeable future. Even after the pandemic is over, all this data should still be out there for analysis purposes. So my specific forecasting approach, my model is called COVID Complete, is really based on the timing of how the disease progresses. And if you look at the way the disease progresses, this will seem a little obvious at first, but on day 0, someone gets infected. And a couple days later, and the research on this is reasonably solid at this point, they become contagious. They don't become contagious the instant they're infected. They become contagious a couple days later. At some point after that, around 4.5 days on average, a person develops symptoms. Now, early in the pandemic, they would get tested some indeterminate number of days after they develop symptoms. One of the nice things, or the accomplishments of the pandemic, has been, as we have become more sophisticated in testing, contact tracing, sensitizing people to that they might have been exposed to someone who's infected. In some cases now, the testing occurs before the symptoms show up. And so there's some variability in the timing here. And ideally, we'd like to push that test point as far to the left as possible. And of course, the ideal is to push the test to the point before contagiousness begins, so that the person knows that they have the disease before they're even tested. And then at some point, contagiousness ends, and then either the person dies or they develop antibodies. And this happens basically about 3 weeks after the infection begins. Now, of course, there's variability around all these numbers, but for forecasting purposes, the variability matters somewhat. But what really matters is just knowing where the center is. And so if I can know the number of tests as of a particular date, the number of positive tests, and then I can know about how long there is between positive tests and the time that someone dies from the disease, and I can know about how many people tend to die versus how many people test positive, then I can accurately predict the number of deaths 14 to 21 days in advance. And that's been a bit of a moving target over the course of the pandemic, not so much because the disease has changed, but because the reporting timeliness has changed. And as the reporting of tests has sped up and the reporting of deaths has gotten a little bit more reliable, the relationship between the timing of the test report and the timing of the death report has shifted over the course of the pandemic. And so at the national level, we can do this with terrific accuracy. And the good models are averaging about 10% error at the national level in the death forecasts on the 1 to 4 week horizon. At the state level, we can do it with pretty good accuracy, but it's definitely more variable, and that's largely due to the fact that reporting at the state level just varies a great deal from state to state. So that's the way that COVID Complete approaches forecasting. Other models do approach it differently. So that is the way that COVID Complete and some other models approach this. So that theory all sounds good, right? How is it actually working? The way it's working out is pretty well for COVID Complete. This chart shows how well the different models that have contributed around 80% of the possible forecasts over the period from the time COVID Complete started contributing forecasts on August 24th up through the end of last week. How well the different models have done on the national forecasts. These are sorted from most accurate on the left to least accurate on the right. As you can see, COVID Complete has been the third most accurate national forecast model over that period. And this is in a pretty interesting group of organizations. Some of these organizations are really high profile, very well known. And one of the reasons I got involved in this activity in the first place was there were organizations that should be doing an awesome job that were just not producing very reliable forecasts. And that has continued up until the present day. So there's the Ensemble model. The Ensemble model has performed in the top quarter of the groups. In any given week, it's typically not the most accurate, but what it does have is the ability to be consistent over time. And so a lot of these models really are highly variable in terms of being really accurate some weeks and really inaccurate other weeks. The Ensemble model is never super inaccurate. It's sometimes pretty accurate, but it's quite consistent. Other high-profile groups that I'll call attention to, USC, Columbia University, University of North Carolina, they have a joint team. Johns Hopkins University, the official source of much of the data. Interestingly enough, you'd expect Johns Hopkins to be at the top of the leaderboard for forecast accuracy, but they really haven't been. IHME, which has gotten a lot of press in the US, they were advising the White House for a long time. Their forecasts have not been very good. They've had some just wildly inaccurate forecasts, which unfortunately have gotten a lot of media attention. Johns Hopkins, another one from Johns Hopkins, another one from Johns Hopkins, not very accurate at all here. Los Alamos National Labs, one of the national research labs in the US, really, they're doing better recently, but for a long time, their national forecasts were quite poor. UCLA, not on the leaderboard at all. And so COVID Complete's position has ebbed and flowed a little bit, but it's typically been in the top 5 since it began, and I think that's a pretty good accomplishment. The main reason I mention that is to give myself a little bit of credibility when I talk about what lessons we've learned. If I was at the bottom of the pack, then I don't know how much credibility I would have in saying that we learned any lessons from COVID forecasting. But since it's done pretty well, I think there is some basis for saying we can apply some of these lessons to software. So lesson number 1, as it applies to software estimation, is use historical data. The most common forecast model is called SEIR, which stands for susceptible, exposed, infected, and recovered. This is the established epidemiological model. The interesting thing about this is that I think some of the organizations that started with really mature, very well-developed SEIR models that were based on influenza forecasting actually took a long time to adapt their assumptions appropriately for COVID. In a way, they started out at a disadvantage because they had an existing model, because it took them a while to recognize that the assumptions they were using were not applicable to COVID and needed to be changed. And so they're kind of dug into the mistaken assumptions and took longer to realize they were wrong than somebody like me who is starting from nothing and could just look at the problem fresh and come up with a fresh set of assumptions. And that's been one of my personal learnings. One of the things that happens when you contribute forecasts into the CDC is there's a weekly call for all the forecast teams and the CDC, and you get to listen to commentary from the different teams. And there's some amazingly sophisticated models here that don't actually work that well. And the good news is those models have been improving over time as a rule, but it took way longer than it should have for those to get to a point where they were somewhat accurate. There are a variety of methods being used for forecasting. Some of the teams are just using massive data sets, 500 million records that could be based on cell phone data usage or various other things that you've read about. Some teams are using machine learning, some are using AI. There's lots of Bayesian analysis, Monte Carlo simulations, et cetera, et cetera. With the number of teams who have been contributing, there just has been a universe of different kinds of methods. My forecasting method is really just based on looking at the number of positive tests and then applying a ratio and calculating a number of deaths from that. Pretty simple approach. The black line on this chart shows the what's called the case fatality rate, which is basically just the number of positive tests, or rather the number of deaths divided by the number of positive tests some number of days earlier. That number of days earlier has shifted over the course of the pandemic. Currently, I'm using 21 days as the gap between the positive test and the death. But if you look at the black line, it's been pretty consistent, really for about a year now. It had dropped very, very slowly from about the beginning of, or the middle of June, well, really more like the beginning of July, through about the middle of March, and it wavered some. A lot of this is just due to reporting irregularities, but it's been consistent enough that it's served as a reliable basis for making pretty accurate forecasts on the kind of timeframes that I've talked about. So basically, COVID Complete counts positive tests, and if anyone has read my estimation book, my rule of thumb is you count first. If you can't count, you compute, and if you can't compute, then you apply judgment. In this case, there is something we can count. We can count positive tests. We calculate the current death rate or case fatality rate, multiply tests by the current CFR, and that's how we get the results. We have a few models that are using this approach, and among the top 5 models, at least 2 of them are using this kind of approach based on positive tests and the lag from positive tests to deaths. So this approach has worked pretty well. There are other approaches that have worked as well. The most accurate model really for several months now has been Carlin's model, and that is definitely a different approach that doesn't use this technique. So it's not the only accurate approach, but it has worked pretty well. So I think the software lesson learned here is use historical data. And in the software context, the historical data accounts for most or all of the factors that affect your team's productivity. And it has the additional advantage that it's not subject to estimation bias. So like velocity in an agile context is a tremendously useful estimation or forecasting tool, because the velocity that's calculated for your team includes implicitly all the assumptions about what the productivity influencers on your team's output really are. And a lot of times if people come up with more elaborate models where they have lots of adjustment factors and so on that are not based on historical data, then they just make mistakes in applying those adjustments. And if we can really put our effort into making sure our historical data is accurate and that it means what you think it means, then that gives us a good basis for using that historical data to project effort forward and make forecasts about schedule and amount of functionality we can deliver and so on and so on. Second lesson learned is keep control knobs to a minimum. And I refer to adjustment factors on an estimate as a control knob. As I mentioned a moment ago, different groups have been using a lot of different methods, like 500 million, or a lot of different methods, like 500 million records in the data set. Mobility data. Mobility data has gotten quite a bit of press, but the teams that use that have not contributed very accurate forecasts. They've been in the bottom quarter in terms of accuracy. Machine learning has been a reasonably successful approach, and the pre-existing infectious diseases models have operated, as I said, not very well at first, better as time has gone by. And I go back to this quote from J. Scott Armstrong in Principles of Forecasting, a book that came out in 2000. He made the comment that one of the most enduring and useful conclusions from research on forecasting is that simple methods are generally as accurate as complex methods. And that's really counterintuitive for analytical people, I think. I think for analytical people, we tend to think that the more adjustment factors, or I would say control knobs, that we can put on a forecast, the more accurate we're going to be able to make the forecast. And what we think is that as we can tweak the dials a little bit, that every time we tweak the dial, that we're going to make the forecast a little bit more accurate. But I think what really happens in practice is every time we tweak the dial a little bit, we insert some subjectivity or bias into the forecast and get away from the pure use of historical data. And so what we're really doing is inserting error into our forecast rather than improving its accuracy. So the software lesson learned here, I think, is keep control knobs to a minimum. I favor simple models where I can understand the data I'm using, and understanding the data you're using is a non-trivial mission. It takes a lot of work to really understand what the data actually means. I'll get into that a little bit more in a minute. And in general, keeping control knobs to a minimum means using what we call proxy-based estimation. That is, we count one thing, we use a known relationship between that thing and whatever it is we're trying to estimate or forecast, and then we calculate the thing that we're interested in based on the count of the thing that we can know. And so in software, the things we can count and use as proxies are things like story points, stories, features per week, per month, per sprint, and so on. So if we can keep the control knobs to a minimum, use a simple count and then a calculation or conversion, then we tend to get more accurate results. The next lesson learned, I would say, is accuracy first, precision second. And this has been a career-long mission of mine, is to get people to understand the distinction between precision and accuracy. Accuracy refers to, did you hit the target? Precision refers to simply how specific or exact is the quantity that you're using to express your forecast. So this chart is a chart that I produce on a weekly basis, and it shows the results of the 95% prediction intervals for all of the forecast models. And as you can see here, the accuracy is on the x-axis or the horizontal axis, and the precision is on the y-axis. So in both cases, being higher and to the right is better. The ideal forecast would be up in the upper right corner. And so because this is supposed to be 95% prediction interval, the ideal here would be to capture 95%. And in this particular instance, COVID complete is actually pretty close to the 95% line, and so this particular period it did pretty well. Now ideally, we would have all of the points clustered around that 95% line. But as you can clearly see, the points are not at all clustered around that 95% line. We have quite a few that are spread out way, way lower than 95% capture rate. And we have some that are under 50%, quite a few actually, that are under 50% capture rate. And so the accuracy is just not here. And what we have instead is a lot of points that are high on the precision scale. So they're very precise, but they're not accurate because they're not capturing anywhere close to 95% of the actuals. And so what we've seen in this context with these forecasting teams is really what I see in software as a classic confusion between precision and accuracy. They think by making their forecast ranges really narrow, that somehow is going to make their forecast more accurate. It doesn't. It doesn't make them more accurate. It just means they miss the target they're trying to capture, and they confuse exactitude or precision with accuracy. The other thing that's a little bit interesting is one of the really interesting takeaways from this massive data set of forecasts versus actuals is I've been able to look at how much accuracy can you get. In other words, what kind of capture rate can you get for a given level of precision? And if you look at that shaded area, the curve across the top right of the graph, that represents an area in which a very, very small number of forecasts have ever fallen, because it essentially represents an impossible combination of precision and accuracy. And so these forecasts that are shown inside the orange rectangle here are essentially forecasts that have too much accuracy, rather too much precision, to be able to get to the 95% capture rate level of accuracy. And they need to relax their precision, make their ranges wider, so that they can get to a 95% capture rate. And you'll notice that this chart shows the period ending January 23rd. I'll show you a chart in a few minutes that ends more recently. And in fact, the teams have gotten better at this over time. So the software lesson learned here, I think, is accuracy first and then precision second. We make it accurate and then we tighten up the range. But the first order of business is getting accuracy first. So we want to avoid presenting estimates that mismatch accuracy and precision, such as estimates that say this release will take 4 sprints plus or minus 3 sprints. The next lesson learned is understand the variability in your data. And we have had a ton of issues with data for COVID forecasting, and this has been something I got clued into and frustrated by very early on, and it's become a very common feature of the calls on Tuesdays that we have with the CDC. One of the issues we have is spikes or corrections. States make corrections in their state level data. Washington State, my state, has been one of the worst offenders in this category. A year ago, more than a year ago, we had a correction, a backfill on our death data. More recently, we've had corrections on our positive test data. And as of right now, as of this moment, we have a backfill of about 3,000 positive tests that haven't been back distributed anyway. And so that's making the pandemic this week in Washington State look worse than it is because of just dumping a bunch of old data into the data pool. And this has been a common feature of the pandemic. I'm not going to go through this list in detail, but just to give you an idea of how pervasive this dynamic has been, these are the corrections that have been made just in the past 7 days. And this is something that people weren't paying a lot of attention to until about 2 months ago. And then finally, we started actually getting regular updates and regular reviews of where the data corrections were. But for a long time, the forecast teams were just taking charts like this and accepting these charts as if those were the ground truth. And in fact, they're not the ground truth at all. They're actually a combination of ground truth and corrections. And those have not been clearly delineated for until fairly recently. Other kinds of issues we've seen through the pandemic are most states don't report on Sundays. And if you look at the graphs, one of the reasons there's so much unevenness in the graph is that some days don't get reports. We also get variation in data reporting by day of week. So when you don't report on Sundays, then you have to catch up later in the week. We also get variable reports around the holidays. Last year, around the US holiday of Memorial Day, we had no reporting on that Monday, and so catching up later in the week. We've seen the same thing over the US holiday of Labor Day, no reporting over that weekend, and so catching up later in the week. Thanksgiving weekend, same thing in the US. Christmas, same thing. And so what I would say is that I go back to Deming on this and say this really looks like special cause and common cause variation to me. We have special cause variations, including deaths that have been wrongly classified, that get reclassified later as either previously classified as COVID, later classified as not from COVID, or vice versa. We've had the wrong kind of tests dumped into the data pool where we get antibody tests combined with PCR tests and then either backed out later or added back in later. We get lots and lots and lots of data that's reported on the wrong date and corrected later. But we also have common cause variation in Deming's terms. That is variations we can expect. It doesn't just arrive unpredictably. We know that there's a weekly reporting cycle and we can adjust for that. We know there's going to be under and over reporting around the holidays, so we can adjust for that. And so I think in software, the takeaway is understand the variability in your data. In software, we also have common cause and special cause variations. When we look at variations in velocity, that's a question we should be asking is, how much of this variation is due to special causes like someone's personal schedule, taking a vacation, or rather getting sick unpredictably, or taking a vacation, which is predictable, holidays and so on, which are predictable, training days, which are predictable, or just problems you run into, which maybe are less predictable. Next point I'll talk about is to minimize the differences between reporting and ground truth. I've hinted at this quite a bit already, I think. But I think it's important to understand we're really working with 3 entities, not 2. We'd like to think that we're working with ground truth and that the ground truth forms the basis of our forecast. But because we've got all this variability around when things get reported and how accurately they get reported and corrections that occur to reporting later, the kinds of dates that we're talking about in my forecast model are not the dates that the events occurred, it's the date that the event got reported, and those are not the same thing. And so really we're working with 3 entities, which is the ground truth, the forecast of what ideally would be based on the ground truth, but really we don't have the ground truth, we have the reporting of the ground truth, and that inserts some uncertainty or some error, which has been really kind of a plague on forecasting for the duration of the pandemic. In software, I think we can take some actions to minimize the differences between reporting and ground truth. In an agile context, we see a lot of examples of this. Do you actually finish the stories each sprint? If you're giving yourself credit for a story and it's actually not quite finished, then you're inserting a gap between the ground truth and your reporting of the ground truth. Do you change the point values of stories after you've completed them? You say, yeah, we assigned it a 3, but it really felt more like a 5, so you change it later. That inserts some distance between the ground truth and the reporting. Did you really meet the sprint goal? Or one of my pet peeves in the way that Scrum has evolved is to say that we meet the sprint goal that isn't the same as whatever the specifics of the original sprint goal were. So did we really redefine the details so much in meeting the sprint goal that we didn't really accomplish what we set out to accomplish? And are we accounting for weekends and holidays and training and so on in our estimates and plans? So I think we can take active steps in software to shrink this gap. The final lesson learned that I'll talk about today is closing the loop. This is something that has been important to me from the beginning of the pandemic. I am a feedback junkie. It doesn't make any sense to me to do something and then not check on how well it turned out. And particularly when we're talking about forecasting, I want to know whether my forecast was any good or not. And that's really the basis of improvement. In Agile, we talk about inspect and adapt. You have to do the inspection or you're not going to be able to adapt meaningfully. So for my forecast model, I publish these charts on about a daily basis. It's probably really more like four or five times a week. But this just tracks how my forecast is doing compared to actuals. So this is a chart that finished a couple weeks ago. But you can see on a daily basis, I'm looking at how far off was reality from my forecast, and that helps me to see how well my model's doing and if I need to make changes. This chart, which I presented earlier in the session, is something that I had to produce. This was not being produced by any of the forecast teams. As I got into these Tuesday CDC calls, my impression was that this was a highly academic exercise for a lot of these teams. They weren't actually concerned about the accuracy of their forecast models. They were concerned more about learning something about artificial intelligence or machine learning or working with large data sets, and they weren't closing the loop on how well their forecasts were doing. So I started publishing data like this, and eventually some of the other groups started doing that too. And I think that's led to an improvement in how a lot of these teams have done. And in particular, one of these groups has moved from the bottom quarter into the top quarter on a pretty consistent basis. And a lot of that has to do with simply closing the loop, set up the feedback loop so the teams can see how they're doing. So I showed this chart a little bit earlier. Really not very good, right? But this is what this chart looks like now. Now, earlier, we had not that many points clustered around 95% capture rate for the 95% prediction intervals. An awful lot of points were way out there in kind of an outer space and with nowhere near a 95% capture rate. Now, we have most of the teams actually clustered pretty well around the 95% line. I think the precision is not great, but this is the way that the improvement should work. We get accuracy first, and then we work on precision. And so most of the teams have, in fact, moved to a place where they're pretty accurate. And so now the goal really is to work on the precision. We don't have that many teams left that are still having low capture rates relative to the target. So the software lesson learned here should be pretty straightforward. That is, close the loop, compare the estimates to the actuals, make sure you understand how well you're doing. When there are gaps, do a gap analysis, see why the gap was there, and understand what you can do different to improve. And then you iterate on that process until you actually are forecasting or estimating well. And I would say this is arguably the most important point in this talk. If you don't do anything else I've talked about, but you do this, you close the loop, you make a point of seeing how well you're doing, and then you investigate how you can do better. It's essentially applying the Agile principle of inspect and adapt. And if you do that with discipline, then really the rest of the points in this talk will follow. You'll get to the point where you understand, the way to improve my forecast is to use historical data. I need to work on accuracy first, precision second. You can get to all those other points simply by following this point of closing the loop and making sure that you are tracking how well you do. So to summarize, I think we've got 6 lessons learned. I didn't start out my COVID forecasting thinking there would be a lot of applicability to software estimation. But as time has gone by, the two situations actually look pretty similar to me. Number one, use historical data, avoid using judgment where data is available and you can use that instead. Keep your adjustment factors or control knobs to a minimum. Favor simple models where you actually put the emphasis on understanding the underlying data, which, as I've described, can be fairly difficult to understand. Favor accuracy first and precision second. Make sure you understand where the variability in your data is coming from. Make sure that you understand what your data really means. And that's what when I say minimize the differences between the reporting and the ground truth, you could summarize that by saying understand what your data really means. And then finally, the most important point, close the loop. Make sure you understand how well you're doing. Background on a lot of this is in my estimation book. There's also lots of detail on my COVID-related website. All this is available from stevemcconnell.com. I've published some articles on Medium. I've also got a GitHub site that is linked earlier in the presentation that has a lot of the evaluation data that I've talked about. And at this point, I think we got like 2 minutes left for questions, so I'll turn the microphone back over to our host.
Mm-hmm. Yeah. Okay. So thank you very much, Steve, for that great presentation. I think it's wonderful that we're able to increase the accuracy over time, as you showed here. Has this model, the COVID complete model, been considered also for making public health decisions during the current pandemic? Has it explicitly been used?
I think there's the answer on this really is surprising. I'm sorry, I'm getting some feedback here. It's surprising the degree to which none of the models have really been used for public health decisions. The IHME model, which is one of the least accurate models, is the one that's gotten the most visibility for public health decisions. As time has gone by, I think the models have gotten a little bit more visibility. But one of the interesting features of the CDC calls is the occasional comment that we had the opportunity to brief the Secretary of Health or somebody like that. But those comments have only come up a couple of times, so it's been a little baffling to me that the forecasts haven't received more attention from a public health point of view than they have.
Mm-hmm. Interesting. In the software estimation, it seems like a huge factor is really the individual's capability and I guess their influence on the velocity. My feeling is that with the COVID forecasting, you don't maybe have so much personal influence the individual persons. Could you speak to that point a bit? Is it more that the way a whole state would act is maybe not so dependent on individual capabilities, or some kind of difference there?
I think there's a pretty good analog there, and I do think that the analog is the states versus the individuals. I agree with the point that there's high variability at the individual level in software, of course. At the state level, we also have high variability. The variability is partly in reporting. We have a couple of states that are reporting deaths only weekly at this point. The smaller states like Wyoming reports deaths only weekly, and some states report every day, including on Saturdays and Sundays. So there's individual variability, if you will, at the state level. The thing that's similar is that in COVID, as we roll up 50 states plus District of Columbia, we get more accuracy in the aggregate than we do at the individual state level. And that's basically partly, I think, attributable to the law of large numbers, which is just when we combine a whole bunch of individual forecasts, there's some errors high, some errors low. They cancel each other out to some degree. So we get more accuracy at the national forecast level than at the state level. At an intuitive level, I think some people would assume you get more accuracy in the smaller detailed forecasts, and that's just not the case. It's more accurate for the national forecast. Same thing applies to software, which is it's harder to estimate the work of one individual, but when you get a group of individuals and those individuals are performing in a particular context, now we get the team dynamics where you get highs and lows canceling each other out. And then we also get constraints that are imposed by the organization in which those people are working. And so what you usually find is that historical data, where velocity is the most common example of historical data, actually ends up being pretty reliable measure for forecasting purposes, as long as you understand what the data is and you're not playing games with it. The issues that teams run into are issues like changing the